Okay, so yeah, we can get started. So today, yeah, it's my pleasure to introduce Professor Ruoyu Sun. Professor Sun is assistant professor in the Department of Industry and Enterprise Systems Engineering and affiliated with Coordinated Science Lab and the Department of ECE at UIUC. Before joining UIUC, he was a visiting research scientist at Facebook AI Research and was a postdoctoral research at.
So this is based on the recent work just to accept to NeurIPS. And you probably have heard about GAN. It has achieved a great success in image generation, for example, in image painting, in generating bags, or even generating dancing. Now our motivation is not try to advance the application, but try to understand the theory behind GANs. One big issue of GAN is that it's very hard to tune. And the current state-of-the-art models, for example, big GAN or style GAN, they all require a large number of GPUs. And actually, for most people in academia, you don't even have the resource to train big GAN. Now, we hope that theory not only help us understand the training of GANs, but also hopefully in the future can make it training much easier for everybody. And this happened to neural network training for supervised learning. That like 20 years ago, training deep learning in the neural network is magic. That some people say that only 2 or 3 groups can train neural networks at that time. But nowadays, almost everyone knows how to train it. And why they work are partially understand. I have written an overview for supervised learning, but for GAN, we don't have such understanding yet. Now, what's in this talk? If you're a GAN researcher, I will show you how to understand the global dynamics of GANs, maybe more understanding, not full understanding, but more. And for practitioners, we will advocate a GAN class called R-GAN. For general audience, we will provide some simple intuition and toy demo of how GAN works. And for pure theoreticians, we'll highlight that the one message is the power of equilibrium analysis, which is a generic trick in all dynamic system or optimization analysis. And another key message is global versus local analysis. Now, our contributions are the following. So in theory, we show that the standard GAN, the original GAN by Goodfellow, has exponentially many bad basins, and each of them corresponds to mode collapse. So this provides a optimization description of mode collapse. And we show that the simple modification has no bad basin. In experiments, we showed that with only 2 lines of code change, you can get better performance. For example, it's more robust to data set, to the width, and to initial point. And we can also explain the training process of simple GANs by the theory. Okay, a quick review. So the goal of GAN is to generate data distribution that is close to the underlying distribution based on samples. For example, if you want to generate Van Gogh paintings, you can try to mimic you can just watch the Van Gogh painting and try to draw it and ask a master to provide feedback. So an important thing is that there's no concrete loss function in the mimicking process. So you need to get a critique. So in GAN, people use neural networks as the critique. So instead of minimizing a general loss function, this loss function is designed to be the maximization of an outcome of a discriminator. Now, why do we highlight this message? Because our whole paper is based on the following view. Min-max optimization is a special case of optimization in the sense that it's minimizing an objective function. Although this objective function is complicated, is a maximization of something, but it's still a function. Okay, so instead of going to the Nash equilibrium or complicated min-max games, we can still come back to the original min-max minimization problem and check the minimization problem. For example, for the sanity check, you can show that actually Goodfellow shows this. The loss function is minimized if and only if PG is in this sentence, we actually view the loss function as a single function. Okay, there's a lot of research recently. We can separate them into two parts. One is on the statistical analysis. For example, the original Goodfellow paper has a connection to JS distance, Jensen-Shannon distance, and the famous Westerstern GAN paper relates this to Westerstern distance. And there's a well-known paper on generalization bound and so on. In terms of optimization analysis, people focus on the local analysis or the behavior around the local minimal stationary points. And the reason is for mean max optimization, convergence to stationary point is not easy. So this requires much effort. However, there's still missing part in the whole story. This bridge is from Goodfellow's tutorial. I recently noticed it after I read the paper. So we can divide the process of understanding optimization as few steps. First is global minimum desired. Okay, this is sanity check. Then, is there a bad local minimum? The next step is converge to what? Do you converge to local minimum or converge to critical point or something? And the final step is how quickly, the convergence speed. In traditional convex optimization, we only check O3 and O4. Well, sorry, in convex optimization, you only check O4. There's not much issue about converge to what. In non-convex optimization, you need to check O3 and O2. And O1 is about the general application of optimization to any field. Now, we focus on actually O2, which is one step before converge to what. Now, there's another dimension that we can explore in the theoretic space, again from Goodfellow's tutorial. His original paper is on the PDF space, on the probability density function space. So the optimization variable is a probability density, is a function. And the second step is to check the generator function space. I will explain a little bit later. Actually, there's a very important difference between S1 and S2 that is mostly ignored. And the final step is parameter space. So the parameter space is the space that everybody's working on, that you're training the parameters of neural networks. But for theoretic analysis, you may need to understand PDF space first, and then function space, and then parameter. So we'll cover the S2 and S3. So here is a table on the 2 dimensions. As I said, Goodfellow is about PDF space with sanity check and actually some global analysis, O2. And most of works in optimization is on actually this corner, that is parameter space, but with local analysis. And some works on the PDF space, but on the global convergence. Now there's very little work on the function space or parameter space for the global analysis. And we cover this part. Actually, the sanity check is pretty simple. So the major difficulty lies in this part. So whether global minimum, whether local minimum are good in the function space. And once you have done this, you can extend it to parameter space. Okay, any questions so far? Okay, and there is an analogy between GAN research and supervised learning research. So what have people been doing for supervised learning can be divided into representation, optimization, generalization. Optimization is especially complicated, that there are multiple issues. In my survey, I have divided this and put a figure, how people have resolved these issues using different methods. And I think we have pretty good understanding of supervised learning, not fully, maybe 30%, 40%. But for GAN training, we only have maybe 5 or maybe even 1% understanding. And we can follow the same pipeline to understanding different parts. And as I said, global issue, which has been studied in supervised learning, was missing in GAN training mostly. So that's why we feel like this is a big gap. Now, before going to the details, we want to talk about some conceptual change of the paradigm. So this is one of the dimensions I mentioned earlier, going from PDF space to the generator function space. But it's actually about empirical loss versus population loss, a very, very classical topic in statistics. So one of the major theorem of Goodfellow is the following. The function is a convex function in PG. So what does it mean? It means that the loss function is a function of a PDF or probability density function. So it's a function of function. Actually, it's a functional. And then you can easily prove it's convex. Now, because of this convexity, people really like this formulation. And there are quite a few papers, including some of the best theoreticians in the field, and also some recent empirical papers published very recently. People are still using this formulation to justify their formulation. Or so this is probably the cleanest way of writing a theorem about GAN. And why? Why do people do this? Because this can convexify the problem by viewing the problem in PDF space. Now, to let you understand the essence of this approach and also the issue, the essence is that any linear function of the probability density is convex. This function, this answer may looks a little bit complicated. Let me give you a very simple example. The essence is just one line. If you have a Bernoulli variable with two probability P1 and P2, and then expectation can be written as in this form, P1, A1, P2, A1, A2 can be two arbitrary given values. Now the claim is this function is convex in P. Why? Because it's a linear function of P. So this is very straightforward and very trivial. This is a optimization 101. Any linear function is a convex function. But if you write it in this following form, expectation of something is convex in PG, it looks like a little bit fancy or complicated, but it's not. It's not complicated. It's trivial. And this is a little bit strange in the sense that if you change fy to an arbitrary function like this, sine y squared plus 1 and cosine y, this is still a convex function in PG. Okay, that's the issue of this approach. It is good. It is useful. It helps us understand the approach, but it does not utilize the structure of GANs at all. It's basically true for any function. So we think is probably important to understand empirical loss. Then we want to view this empirical loss in the function space. Now, instead of the common figure, you probably have seen a Gaussian distribution figure in GAN blocks. We viewed it a different way, that there are a bunch of true data points, which are X, and you want to generate a bunch of data points Y, and you want to move this Y so that they match X. You can think of X as true images, like dogs and cats, and Y's are the images you generate. You want to move in the image space so that they match. Again, the importance here is that we don't have a PDF. We don't have a probability distribution of images. We just have concrete samples of images. This makes things much easier and actually closer to practice. Well, much easier in some sense, that this is just the sample points, but it's harder because of the loss of convexity. Again, the data distribution is a fixed set of data points, and we generate a function space of samples. We want to generate Y to match X. We'll talk about parameter space results later. Okay, any questions so far? So far, actually, we haven't gone to any details of GANs. We are just talking about high-level things. Let me give you one of the simplest examples of how GAN works and how GAN fails. Suppose we want to generate 2 points, Y1 and Y2, to match X1 and X2. X1 and X2 are fixed, and Y1 and Y2 are moving. And we have a classifier, which is the red line, to help you design YIs. Now, in the first step, the discriminator can separate Y and X perfectly. And the next step, the generator will move Y to fool the discriminator. So they will move to the right-hand side of the red line. Next step, the discriminator will further move to distinguish the y and x, and they continue. And you may notice in this process, they may be stuck near the points x1. Why? Because at each step, the discriminator doesn't need to move too far away, since the generator is near x1. And the generator also doesn't need to move too far away, because the discriminator is also near x1. So they may be struggled around x1. Okay, that's the new intuition. And that's exactly mode collapse. If you haven't heard about mode collapse, that means that you generate a single mode. For example, in MNIST generation, you only generate it digits 1. Out of all the space of 1 to 10, you only generate 1. Now, you may have intuition that this seems like a local minimum. But we're dealing with a min-max problem. What does local minimum even mean? And how to make it concrete? Now, a little bit surprisingly, this wasn't formalized in this field, to my knowledge. And partially because people think, oh, we have to deal with min-max. And also we learned that a group at Berkeley by Malik, they proposed similar intuition. And using this to claim this is why mode collapse happens, but they give no formal definition or proof of local minimum. Now this shows how non-trivial this is. Although this is one step, just a simple step, but because of min-max, people may be confused. Now, let's present our solution and then talk about the formal definition later. Now, how to resolve this issue? The issue is there is a single criterion for every generated point. Now, and let me give you an analogy in class. If we have a universal criterion that everybody getting 60 points is enough, I'll give you a pass. If it's pass or no pass, then probably most students won't work very hard because you don't gain extra thing if you work harder. Now, instead of a pass or no pass, if you chose the grade, like A to F, or for example, you tell the students that if you get 90 points, I will write you a recommendation letter. Then they have motivation to work harder. Then these students will try their best. Maybe some students can only get 60 points or 80 points, they were stuck there, but some students can get 90 points, they can work harder. And the key here is to break locality by using personalized criteria. Now here is an illustration. You tell Y1 your target is X1, but you tell Y2 your target is X2. Of course, you don't need to tell which one to go to which goal, but just tell them there are two different goals, X1, X2. Then this may break locality and achieve a better global landscape. And then let's formalize this. We consider two different GAN formulation, but instead of considering Weierstrass or least square or something, we focus on separable or not separable. Now we claim that the original GAN is separable in the following sense. The objective function is the sum of two parts, and one part is about the true data points, xi, and another part is about the generated fake data points. And actually, this is nothing new. This is the nature of binary classification. Okay, if you want to do binary classification, people have sum of the losses, and these naturally separable. If you have R-GAN, that means you couple fxi and yi together inside the loss function h. For example, if you use the logistic loss, then you plug this in, you get sum of two logistics. Wait a second, just one logistics, that fxi minus yi in the exponents. And previously, you will have xi in one part and y in one part. Again, we write it as a general form that it doesn't have to be this form. H can be many kinds of functions. We will formalize the definition or the requirement of H. Actually, it's pretty universal. Almost every H function, maybe a little bit the convexity assumption is enough. A little remark here, we proposed this in an early version of the work. Actually, we motivated from another paper we wrote before. And But later we noticed that there's another paper who proposed the same idea, which is not surprising given that there are 200 GANs in the world. And someone noticed this. Is not too surprising to us, but it has different motivation. It is totally statistical and talks nothing about local minimum or global landscape. But the major setting point of that paper is that they have very convincing empirical results of R-GANs. Actually, we have a hard time to try to show that this works well in practice, works better because of people have very good tricks nowadays. But this paper actually finds how to show there is an improvement. Anyway, we'll talk about simulation later. Now, there's another motivation. Actually, our motivation is from Western GAN. So when we read the Western paper, we notice that there's some discrepancy from what they claimed and what is real in practice. And then this motivates us to really look at why W-GAN makes a difference. Actually, there are two differences. One is changing logistic regression to linear. Another is to couple X and Y, which is kind of hard to find because Western is a special case that is both separable and coupled because it's a linear function. So linear function you can say is coupled and linear. And we claim, actually because we have another paper that we couple X and Y in some way and it works well. And we conjecture the coupling is the key or is more critical than linear. So changing this log to linear is less important. Now, if you only keep the log part, but use the coupling trick of W-GAN, you get RS-GAN. And we suspect this works better for W-GAN, and actually it does in many cases. Due to time limitation, I cannot talk about what's the problem, what's the issue in W-GAN. This actually is a even deeper issue we haven't touched in this paper. But anyhow. And one comment here that many recent papers do not use W-GAN, they use hinge loss. So there's another evidence that what W-GAN claimed. So W-GAN claimed JS-GAN GAN is bad because some distribution issue. That claim is not well justified. Actually, people don't need W-GAN to get SOTA results. Okay, any questions so far?
Or we can ask a question after your talk.
Okay, sure. Let's talk about formal results. So we start from 2-point example to give a concrete theoretical result, then talk about general result, general empirical distribution. Now, to understand 2 points, we identify 4 patterns. There is a perfect pattern that you generate 2 points exactly, and there is a bad pattern that 2 points do not match fake points. Now, these 2 cases are easy. Okay, so if you know that your algorithm probably won't start at this state 2, you will get something. The challenging issue is that you generate partial data, but you don't get all of it. So there are 2 cases. One is mode dropping, that you get 1 point correct, but another point is incorrect. Another is mode collapse. So every image of yours looks real, but they're just one small pattern of it. So mode collapse is even more challenging than mode dropping. So for the terminology, some people call both state 1B and 1A as mode collapse. And, but some people call this as mode dropping and 1A as mode collapse. We kind of following this second terminology that we call this kind of case mode collapse, and this kind of case mode dropping. Okay, here is the first formal claim. Is actually a calculation of all the values in this landscape. This calculation itself is not very meaningful. It's just a bunch of values. But there is a corollary out of this, that there is strict local minimum, or called basin, in JS-GAN GAN, which is a mode collapse. So if you generate y to be x1, that is strict local minimum. Now to see this, we visualize it in the following figure. The landscape of JS-GAN GAN is like this. Of course, the global minimum is S2, which is a perfect generation. And if you start in the bad state, you have a very high loss. But for mode collapse and mode dropping, there are different values. So mode collapse, you will have a value of about minus 0.48. Maybe you can remember this number. I'll use this later. Very at the end of the talk, we'll talk about this number. So there is a bad basin here. But if you check RS-GAN, these two values are flat. So they're the same value, there's no bad basin. Now we use the terminology basin, we don't use local minimum, because technically speaking, in both cases they are bad local minimum. Because actually local minimum and strict local minimum are different. Many people are confused about this. But to distinguish it, we highlight JS-GAN has a strict local minimum or basin, and R-GAN does not. And the intuition is that JS-GAN views mode collapse as worse than mode dropping, and R-GAN views them equally bad. If it's equally bad, then there's a chance to escape. To give you more intuition about what basin is, I will give you two figures. So the non-strict local minimum is like a river in the valley. If you're riding a boat in the river, you may finally go to the sea. There's nothing to stop you from going to the sea. It just takes longer time. Basin is like a barrier lake. If you ride a boat in this barrier lake, you will never go out of the lake. Okay, that's the difference. Now, if you use gradient descent, of course you will have to descend. But in practice, people using noisy gradient descent or SGD. So so there's a chance to going to the sea. Or another view is if your starting point is far from, okay, let me forget about what I said. What I said just now about noisy gradient descent is purely theoretical. In practice, I'm sorry. So actually, it's not. So there are actually two perspectives. One is about noisy gradient descent. Another is about where to start. If you start from high on the valley, in the left-hand side, you can go to the sea, and the right-hand side, there's still a little bit chance of going to the sea. If you're a very good skier, you can jump upwards. Well, which is difficult, but it's possible with some help. But in most cases, basin is hard to escape. You will fall down to the lake. Okay, so you can view noise gradient descent as someone is skiing, but he has some ability to going up a little bit, not just going down. Okay. In any case, basin is much easier. Is much harder to escape than flat local minimum. Okay, now have understand what is basin. Let's state the formal result. This is the first major result in the whole talk. The first theorem is that under minor assumption on H, every mode collapse pattern is a suboptimal strict local minimum. So in total, there are n to the power of n minus n factorial basins, which is exponentially many basins in separable-GAN landscape, including JS-GAN. So in words, mode collapse equals bad basin, at least in the function space of empirical loss. And this, there is one-to-one mapping between them. Now, if you go to R-GAN, the theorem is that there's no bad basin. In fact, we prove a slightly stronger result. It's not just a no bad basin. In fact, you can go to the global minimum through a non-increasing path. We call it global mean reachable. You can improve that. For the RS-GAN loss, it is global mean reachable. And as a corollary, R-GAN has no bad basin. Okay. Now, let's talk a little bit about the parameter space result. You may ask, this is about function space, but in practice, we always use neural networks. Can you say anything about it? That extra step is actually is something that people have done in neural networks literature. We can combine them. So if we have the following assumption, it's a little bit technical, so we won't go to details on this. It's mainly for completing story, but for understanding is probably not necessary. But anyhow, for the concrete purpose, we can define the following assumption that if G and F are good enough, we say this have enough of representation power, but actually is more complicated than that. I'll explain this next slide. Under this proper assumption on G and F, you can show that the loss function is not global mean reachable for original GAN. Again, the generator and the excuse me, the generator and discriminator are both parameterized by neural nets in this case. Now in the new loss, you can show is global mean reachable, even using neural nets. Of course, this is not true for any neural nets. It requires assumptions on neural nets. For example, enough neurons, enough width. So over parameterized, to put it in other words. Let's explain a little bit about the assumption. This assumption is actually about the mapping of the path. In words, it means that the path in the function space can be transformed to the path in the parameter space. Actually, this is a very deep result. Well, it's not deep result, it's very deep understanding of neural nets. The whole results in the neural network theory is actually about this, but people don't say it explicitly. For example, the so-called neural tangent kernel result that if NTK is positive definite, people show that this is positive definite for over-parameterized networks. And actually, the real use of this is that you can build a connection between the path in function space and path in parameter space. and with this, you can prove convergence. So convergence is just outcome of this. Some people criticize NTK for using too strong assumption of two wide neurons, like 10 to the power of 6 neurons. In fact, you don't need that much neurons if you just want to prove positive definite. Actually, we have a paper following a different line that for non-polynomial neurons and within you can prove a slightly weaker version, actually a perturbed version of this. And you can transform this to GAN as well. Anyhow, this is trying to tell you that which intuition or which message of neural networks we borrowed is actually about the about the connection between function space and parameter space. And actually, people in neural network area may not realize this because they just want to prove convergence. But for GAN, we really need this message. So somehow, in order to understand GAN, we develop some, we highlight some message for neural networks. Let me spend 3 slides on the math proofs before going to the simulation. So here is the key of the original GAN proof. Is actually one line. Is solving an optimization problem with a specific function d. No, sorry, not specific function, but any d in the function space is actually a one-dimensional optimization problem, and you just calculate it. But the key intuition is that if you have a mode collapse, by the original formulation, you will create an extra value minus 4.48. This irregular value creates a bad basin. I call it irregular because it's not a rational number times log 2. Now, if you go to RS-GAN, I can prove that for any case, the function value is a rational number times log 2. And then mode collapse will not create an irregular value, thus creates no bad basin. So the math essence is pretty simple. And I think probably any student can understand these 2 lines in an hour or so. Well, the difficulty to understand the relation between the math and the GANs, but the math itself is not hard. To prove the no bad basin, we require some extra technique in graph theory. It's actually surprisingly more complicated than I thought. I thought it's just 1 line or a 1-page proof, but it actually takes me 10 pages. We need to build a directed graph and then decompose the loss function into cycles and trees and analyze the contribution of cycles and trees. So I will not go to the details, but it's not very hard. It's just if you understand a few special cases that you need to decompose in cycles and trees, then you understand why this works. So in this proof, we don't use too many properties of function h. That is why this is generic for any function h. It's mostly about the structure of the loss, not about the specific choice of h. Okay, now let's explain some experiments. To me, the most interesting part is not the theory. Actually, I kind of know the theory. So all this theory, I kind of know it when I developed the intuition for the 2-point case. But the missing part, the mystery part, for a long time that bothers me is the link between this and experiments. And it actually took me a long time, maybe 1 year or so, to realize the connection. So we want to relate the basin to the real GAN experiments. How? Now, there is important understanding that basins are not black holes. Basins are more like gravity. So what does it mean? Excuse me, computer is stuck. Wait a second. Sorry, my computer is stuck. So the basins are not black holes. What does it mean? Black holes will attract everything near it. Okay. One might think that basins are like black holes that if you fall into the basin, then you will never get out. So if you follow this kind of thought, you would think that JS-GAN will perform very badly. You will be stuck at mode collapse. Well, this happens in some cases, but in other cases, it doesn't happen. So this is why I was confused before, that why JS-GAN even works. So there's some issue with my computer that's why I quit the full screen mode. Let me try again. It seems that I cannot use full screen now. To this, if I use full screen, okay, let me try again. Sorry for the issue. Okay, it comes back. So if you think of them as black holes, then JS-GAN will never work because you will easily stuck at the mode collapse. But in practice, it can work. Now, we interpret it as gravity, that you will slow down training, but it will not make it totally fail. So it takes much longer time to escape deep basin than a shallow one. So you can think of if someone passes nearby black hole, then you can still escape. Even if you fall into black hole, it's not black hole, you fall into this basin, if you have a large enough noise, then you may still be able to escape. So that's why you should slow down training significantly, but not totally make it fail. Now let's check the two figures, two videos of GAN. So the blue points are the true points, and the red points are generated points. We have two clusters. Now I want to generate the red points to match this. You can see that for JS-GAN, it is swinging between the two modes. For RS-GAN, you can see it's swinging for some time, but at some point they split. Now, if you train this for 5 times longer, JS-GAN will be the same as RS-GAN, that it was finally split. So it's much slower than RS-GAN. To understand why this happens, we check the loss function. Now, there's one big issue of understanding GAN is the loss fluctuation. It seems to be strange. Now, in original, in the standard minimization problem, you will see the decreasing value, right? You will see the loss starting from 1.2 or training error starting from 100%, then going to like 5%. You know exactly what's your progress. In JS-GAN or in GAN training, you don't know what it means. Now, I can tell a little bit more about this. Not everything, but it's a little bit more. Why there's fluctuation and why it is stuck here. And if you check the minimal value of this, now how large is it? It's about 0.48. 0.48 is exactly the irregular value we calculated before for JS-GAN. Now, if you check this one, the minimum value is about minus 0.3. Is a rational number times log 2. Actually, it's half of the log 2. So for RS-GAN, you really achieve the values we calculate. Okay, 0.48 versus 0.35. This is indicator that the training has really fall into the bad basin we predicted. Now, to further understand this, we have run a visualization using the two variables. There are two optimization variables in this problem. One is the discriminator, and this discriminator is a function. So the optimization variable is a function. There's another optimization variable, which is y. Y are the points. Okay, so this is a min-max problem with a points being a variable and function being a variable. This is why it's extremely difficult to visualize GAN training. Now, people have done this for supervised learning. You can see how the points move. But for the GAN, how to visualize a function? You have to visualize a function in the function space. Now we don't visualize the function in the function space. We visualize the function itself and see how it evolves. Now, before running this video, maybe 20 seconds, let me explain a little bit. The blue points are the true points, xi's. The red points are the yi's generated points. And the line is the function d. So in this figure, the red point is the variable for generator. The blue line is the variable for the discriminator. And we want to see how they battle. Now, let me explain a little bit about why this evolves. So the goal of the generator is to go to to minimize or maximize. You want to go to, I think, the minimizer of the D loss. But the discriminator want to modify this line so that the red points stay in the lower high region. So they have different goals. That's why yeah, so the red points want to go up, and the blue lines want to push the red points to go down by changing the positions of the function. Now you can see that the red points are going up, always trying to going up. Now, after some training is stuck at this mode, and this mode is exactly the bad basin we predicted in the theory. And the value, let me show this again. So this bad basin will make the training stuck for quite some time, but it will not stuck forever. After some time, you will just quickly escape and converge to the global minima. Let's see the video again. You start from a single mode, generate a single mode, and then this mode will always trying to go to the higher part of it. And after many rounds, there's some chance of going up, but still, you tried very hard, but finally get stuck at a bad basin. And after stocking it for a long time, it may finally converge. Now let's check what's happening for RS-GAN. A similar logic happens to the line and the red points, but the function space is different, okay, which we didn't show here. There's no bed base in the function space, so there's not much struggle. It quickly converges to the global minimum. Okay, if you look at this, this is a struggle for JS-GAN. It struggled for many rounds, attracted the bed basin, and finally the bed basin works, and it's really stuck there. But because of the noise, because the step size is large or something, you can finally escape. Okay, that's why this training can work, but it works much slower than R-GAN. Can we generalize this understanding to general GAN training? We're still working on it. There's some difficulty. It's not as ideal as this plot. You need to consider some extra issues, but at least for this two cluster case, we have we're pretty good understanding of the training process, which is not easy if you don't have this landscape analysis. Okay, hopefully I convince you that this analysis is at least useful for some empirical, for understanding some empirical training. Now let's emphasize the math essence here, that we do not try to understand the dynamics. We don't want to prove convergence. I think convergence is much, much more difficult than understanding the landscape. For GANs, it's just not the stage yet. Now, many theoreticians want to do end-to-end analysis through global convergence with even linear rate, which is great. But for GAN, it's just impossible at this point. So actually in mathematics, one of the major understanding in the history is to try to discard the ambitious goal of understanding everything. Let's understand something. Especially nonlinear dynamics is extremely complicated. So maybe let's understand the equilibrium point first. So this is a qualitative analysis instead of quantitative analysis, which is, by the way, the contribution of Pangari in the history of dynamics. So we ignored it. Of course, in the future, we want to prove convergence. But for now, I'm happy with this landscape analysis. Now, let's talk about some real data experiments. Does it really work in practice? First, there's only 2 lines of code change. I code this myself, so I know this. I'm pretty surprised that only changing these 2 lines to the following 2 lines will make so much large difference. So much different. For other GAN losses, the same change, well, not the same, but similarly, a simple 2 lines of code change will work. Now we make a few predictions based on the theory. First, the simplest prediction is that R-GANs are better. Okay, fine. Of course, we should show it's better in some sense, maybe better FID scores or something. But there are 2 additional predictions. Since we talk about landscape, and the landscape is really related to the overparameterization or the width of neural nets, we predict that for narrow neural networks, the gap will be much larger. And another prediction is that there exists bad initial point that the original separable GANs will fail. In short, we predict that R-GAN will be more robust to data, to initialization, and to width. Now, people have explored the first part, the robustness to data, a little bit. So let me talk about some of the existing achievement of R-GAN. It's not my contribution, but it's people have used it. For example, in super resolution, one of the SOTA called ESR-GAN applied a variant of RS-GAN as a major improvement. And the original, in the other GAN paper I mentioned, R-GAN paper, they show that they can, compared to the original GAN of generating cats, they can generate pretty good cats in, say, 5,000 iterations. And this is the reason that Goodfellow got surprised. Well, I mean, got impressed by this paper, by that paper, which proposed the same loss. So he quoted, they tweeted that this new family of GAN loss looks promising. And I think in his recent paper, LabGAN, he also used this R-GAN. Now we have done this simulation for another high resolution data set. In fact, I would say that the original, this paper didn't perform a high, very extensive experiments because of the high computation resources. We've tried the experiments for LSUN, we find the RS-GAN is much better than JS-GAN in the standard hyperparameter setting. And this is understandable because the landscape issue will be less problematic if you have a low resolution image, because low resolution means that you have enough data. In high resolution, you don't have enough data, then the empirical loss is more important. Now, if you check the FID scores, there's a large gap if you don't use spectral normalization, but use spectral normalization will shrink the gap a lot. That's why we're having a hard time before to justify it. That's why we check the narrow nets. We find that even with spectral normalization, RS-GAN there's a huge gap of up to 12 FID scores. And also JS-GAN performance is very unstable across different random runs, which is a typical case of bad landscape. And we'll also check other losses. As I said, this is universal, not just for logistic loss. It can be hinge loss, it can be least square loss. We checked the hinge loss and found the gap can be as large as 9 FID scores for narrow nets. And we also checked the least square loss. The gap can go from -2. Actually, we're worse than this in the regular case, but it can be 6 points better in the narrows. And we also did a bad initial point experiment that we find an initial point that a regular GAN fails badly. That FID score is about 60 or 93, but RS-GAN is pretty stable in all these initial points. Okay, to conclude, we study the empirical versions of GANs in both function space and parameter space. And we prove that the one case has bad basin, another case there's no bad basin, and we relate bad basin to mode collapse. And in simulation, we show that R-GAN is more robust to width and the initial points, which explains why R-GAN is pretty popular nowadays. In terms of the big picture, that our goal is to identify a non-convex-concave model that is possibly tractable. We know that in neural nets, people are trying to understand why a non-convex problem is tractable. But in GAN, we try to find a non-convex-concave min-max problem that is possibly tractable. And mathematically speaking, our trick is to identify equilibrium points instead of dynamics, which is a pretty common approach. But we just applied it to, again, this high-level understanding. Our future directions is to have a better understanding of GAN behavior. I have to say that there's still a lot of mysteries about GAN training. Even for the 2 points case, for example, we don't know how to formally prove that the fluctuations and how to prove that they can escape. I don't think anyone can do it now, even for 2 point case. So in general, this is about optimization theory for special class of games, not about generic games, because generic games is just too hard, but how to identify the special class. And for practitioners, people are interested in efficient GAN training. The big GAN is so big and our style GAN is too big. How can we make it more efficient and also achieve good result within a reasonable time or reasonable computation resources? Okay, that's all I have for today. Thanks everyone for listening.
Okay, I think we have questions from the audience.
Okay.
So Hamid, can you hear me?
Shall I start from, there's a question about.
Yeah, can you hear me?
Yeah, we can hear you. Yeah,
hi,
we can ask.
Yeah, hi, this is Hamid Krim. Very good talk. I enjoyed it very much. I have a question. It seems to me that you haven't referred anything about the